Dear students, today I will explain a very interesting phenomena and which is called Zeeman effect. As you know that there are some sources which produce line spectrum, and if those sources are kept in a magnetic field, then it was observed that the line spectrum has splits into its components. So how it happens, I will explain it today. Why it is very important. It is also called magneto-optical phenomena. It gives how the magnetic field affects the different states, energy states of the light emitting atoms. So it is very interesting. So now I will explain it to you. Here I am going to explain you. This is a part of the experimental setup. Here this is the telescope, this is the electromagnet, and now it is connected with the battery. So you can see that there is a hole in the electromagnet so that anyone can be able to observe it, which is called position 1. This S is the line spectrum producing source, and this is the another position which is called position 2. This is called longitudinal position, and this is transverse position. So if you see in the telescope, what you will observe that if there is no magnetic field, we just observe one single line, either in position 1, either in position 2. But as soon as we apply a magnetic field through the electromagnet, if we go to the longitudinal position, then we observe there are the two lines components and the central line is missing. And these are circularly polarized lights. Similarly, if we come to the transverse position, what is the meaning of transverse position? That it is the perpendicular to the direction of the magnetic field. So transverse position, we have three lines. Here I am showing that the central one, it has the central one, and in this it is parallel. All the electric vectors are parallel to the direction of the magnetic field, and here electric vectors are perpendicular to the direction of magnetic field, and this one also left one, and you can see that there is a shift from the central line, and which is called the Zeeman shift. So this is the whole idea of the normal Zeeman effect. When you apply a magnetic field, then the single line spectrum without field, it has a components. Now I will explain that at the atom level, if you see, if one electron is revolving in the orbit, so there is a current and it is having area enclosed within its orbit. So this will be orbital magnetic moment, the magnitude of the orbital magnitude, which is I into A. This is I EV upon 2 pi r. This is the area enclosed if you consider that the radius of the orbit is r in a simplified model. So what will be mu L? So that will mu L will be EV r upon 2. Similarly, when one particle is moving in a circle, it has orbital angular momentum, which is mvr. V is the velocity, r is the radius, m is the mass of that particle. So taking this ratio, mu L upon L, this is L. So mu L upon L, we get E upon 2L. Another thing I want to tell you, that you know that when we apply a external magnetic field, then what happens? In presence of magnetic field, the orbital angular momentum L, it recesses around B, which is called Larmor precision. And you know that the value of the Larmor precision is E upon 2m, and B. This is the value of magnetic field. As soon as you increase the value of magnetic field, the frequency will be more. So these are all the background of that, and there is the space quantization. Then another concept is the space quantization. If we apply the external magnetic field, the orbital angular momentum, it has the specific direction in the as per the magnetic field. As you know, for example, if you take L equal to 1, then we have the values which is ml, this is plus 1, 0 and minus 1. So, if it is oriented in the space in a specific direction, so it has a projection on the magnetic field which is called ml. So if you take, so we can say that this is Lz. If you take this is the z direction, magnetic field is applied in z direction. So this is ml. So Lz, that will be ml h cross. The value of Lz will be ml h cross. Now, if we talk like this is from Larmor's theorem, angular velocity omega is this, and this is the projection of orbital angular momentum on the z-axis. That is the direction of the applied magnetic field. So you take Lz mlh cross. So what will be the interaction energy? This interaction energy will provide a change in the energy state, atomic energy states. So that is defined, delta is omega Lz. So just put the values of omega Lz, you will get E upon 2m B ml h cross, which is h upon 2 pi. So what you will get, E h upon 4 pi m B ml. So this is, now you see that this delta E interaction energy, that depends on the applied magnetic field and the values of ml. As you know, for a particular value of L, we have 2L plus 1 ml values. So it means now we have delta E that has 2L plus 1 values. So it gives that any single energy state has the splitted components which is governed by the 2L plus 1. So now, if we take the term value, which is defined like minus delta T, which is defined as delta E upon hc. So if you take E h upon 4 pi m B ml and divided by hc. So you see, and that will give you E B. So if you take the B inside, EB upon 4 pi m C and ml. This is called Lagrange unit. Lagrange factor. So that will be defined by L dash ml for a particular value of the magnetic field. This whole bracket will be constant. So the value delta T, that term value, that will only depend on the value of ml. So here I am showing you the transition between 1d2 state to 1p1 state. Without applying a magnetic field, there will be a single transition. When you apply magnetic field, the ml values that will be split into plus 2, plus 1, 0, minus 1, minus 2. Similarly, this is plus 1, 0 and minus 1. And if you take the selection rule for delta ml, and that is if you take 0 and plus minus 1. So this 0, if you take the 0, so this one, middle one, from plus 1 state to plus 1, from 0 state to 0, from minus 1 to minus 1. So that will give you the, all these three transitions give the same intensity and they will be the same line on the spectroscopic plate. So that will be, if you plot here, you will get a central line, and that is for this ml equal to delta ml equal to 0. Similarly, if you see, you will see that for the delta ml for plus minus 1, you will get these two lines. There are the three set of three lines. So you will get the same three line intensity in a single one. So this one is a parallel one. They are the two perpendicular lines, and this shift is Zeeman shift. So this is explained by all the concepts. It is explained by the quantum mechanics. Similarly, you can also explain it by the classical mechanics. So I request you all to learn this one by the classical mechanics also, from the derivations of classical mechanics. But this is the quantum mechanical explanation. Here you can see that as soon as you increase the value of B, that splitting will be more and more, and it will be large, and that will depend on the value of B. Now I will tell you in my next lecture that if you are going to increase continuously the magnetic field, what will happen to the Zeeman pattern. Thank you.